Hello, everyone, and welcome to part 2 of chapter 19. So now we're going to pick up with white blood cells, platelets, and look at how we stop bleeding. So we'll get into this and talk about it a little bit. So as we start off, let's talk about white blood cells. A typical microliter of white blood cells will contain around 5,000 to 10,000 white blood cells in a single microliter. Now, they come in two types. We'll talk about what's called granular leukocytes. I want you guys to think about and then agranular leukocytes. Now, we're going to talk about what is called granular versus agranular. Think Ben loves money. I always say Ben is granular. He's been granular before. Ben granular. Agranular loves money. So Ben granular. Ben, basophils, eosinophils, and neutrophils are the granular leukocytes, where the agranular leukocytes, which actually have few, if any, granules, technically they all have granules. It's just that what a granule is they may not appear as staining when stained and classified. Agranular leukocytes are lymphocytes and monocytes. Ben granular. Ben granular, basophils, eosinophils, neutrophils, loves money, lymphocytes, monocytes, agranular. Like I said, granules are basically these lysosomes, peroxisomes, things like that. These are compartments that are cellular compartments that have in them chemicals for the immune response, like enzymes and chemicals that are used in immune response. They might contain the leukotrienes, the prostaglandins, your eicosanoids. They might have heparin, which we're going to see is an anticoagulant, histamine, bactericidal compounds, acids, and a variety of chemicals. Now, technically, they all are what we say is granular. They all have granules. It's just when they are stained, the granules might not show up. So just remember, Ben loves money. That's my mnemonic. Okay, let's talk about a differential count. Now, differential count, to remember these, is so basically what we do is we take our cells, we stain them, we count them, and we qualify them. That means I identify them as an individual cell. I say this is this type of cell, this is this type of cell. And it can be classified and counted based on staining and shape. Now, to remember them, remember, never let monkeys eat bananas. That is the order of abundance, is called neutrophils, lymphocytes, monocytes, eosinophils, and basophils. For example, we can diagnose diseases like leukopenia, which is when the number is too teeny. Leukopenia is too few white blood cells. Leukocytosis is too many. It could mean a leukemia of some type. All right, now what are some things they do? Well, one of the things they possess is amoeboid movement. They move like amoebas. They are motile and they attack. They have amoeboid movement. They go after pathogens, disease-causing agents like viruses, bacteria, things like that. They can migrate out of the bloodstream. What they'll do is they'll roll along the lining of a blood vessel, and when there's a gap in the blood vessel due to inflammation response, they will move out of the cells and capillaries and leave to the tissues. This is called diapedesis. Now, right here, you can actually see this, that a leukocyte, what it will do is it will roll on the surface, and when it finds a gap in a capillary, it will go out. I oftentimes like to say diapedesis is basically the white blood cell version of yeet. They yeet out of the blood, the capillary, and go to the peripheral tissues. Now, another thing they do is they exhibit what is called a positive chemotaxis. That is, they are attracted to chemical stimulus. What they're going to do, guys, is they will be attracted to chemicals that are released from like disease-causing agents. For example, a chemical stimulus. When a cell, for example, comes in contact with the pathogen, they release SOS molecules, distress call molecules, molecules that we'll learn about that are used to let the immune system know that there is a disease-causing agent around, and they get attracted to that chemical cue. They also can, many of them can do phagocytosis. Now, remember the phagocytic cells. I want you guys to think pneumophagocytes. Now, where we are in the state of Tennessee, that's something we might say Nemo people. The Nemo people in Washington, they need to get out of there. We might use words like that. It's them. We might say NIM. So NIM. Nymphagocytes, neutrophils, eosinophils, monocytes are phagocytic. They can do phagocytosis. Remember, phagocytosis is cell eating. That's when cells engulf solid things like bacteria, for example. All right. So we already looked at that, and I was like, show it. So do not worry about the actual percentage for my course, but I will ask you to put these in order of most to least abundant, or most abundant. So most abundant, never let monkeys eat bananas, to least abundant. Neutrophils, lymphocytes, monocytes, eosinophils, and basophils. Now, I do talk about it normally of white blood cells in a normal healthy human. We're going to see about 50 to 70% of the white blood cells will be neutrophils, 20 to 30% lymphocytes, 2 to 8% are monocytes, 1 to 4% are the eosinophils, and then basophils are a half a percent to maybe 1% at that. Okay. So they can typically range in those things. Now, the number percentages are not going to be on my test, but the order of abundance will. Now, I do teach the numbers and talk about the numbers so you have an idea and it's there for reference. Now, one of the things I will do is I'm going to describe white blood cells on the test, and I will come in, I will say which white blood cell is da-da-da, 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 has these following characteristics. Which white blood cell might indicate something, things like that. So, first off, we have what is called a neutrophil. Now, look at the nucleus here. The nucleus has multiple shapes to it, so we call it polymorphonuclear. They can have many morphologies to them. The nucleus has many morphs. They usually have 2 to 5 lobes. This one here has at least 3 lobes. And they are granular. Granular. These granules have lysosomal enzymes and bactericidal compounds in them. These are normally first to attack. They are phagocytic, pneumophagocytes, and they phagocytize anything that has antibodies on them. Now, you can see that they are granular. Here we can see all the granules. They neutralize neutrophils by phagocytizing a bacteria. They release their granules and destroy them. This is called degranulation. Degranulation is when a cell releases its contents. It releases its vesicles, and this is, since they're called granules, we call this degranulation. Now, they can release what's called prostaglandins and leukotrienes, pain and inflammation. This is involved in inflammation and controls spread of infections. This also can indicate a bacterial infection, but also may indicate fungal infections, but usually indicates bacterial infection when they are high levels. Lymphocytes, these I say have a naked nucleus. Right here, what you're going to see is, now Ben granular is, so this is not B-E or N, this is loves money. This is agranular. Since they're agranular, you can barely see, there's a nucleus with a thin little halo of cytoplasm around it. We say it has a naked nucleus, is what I like to say, that lymphocytes have a naked nucleus. There are T cells, B cells, and natural killer cells. Now, T cells, they're what we call cell-mediated immunity. They can attack cells like killer T cells, or they go from cell to cell, like helper T cells, or suppressor T cells, or cytotoxic T cells can attack cells, killer T cells, things like that. B cells, they are responsible for humoral immunity. That's in the body's fluids. They can become what is called a plasma cell. And plasma cells will make antibodies in the fluids called humor. Remember that a humoral stimulus is the change in the fluid level of something causes an endocrine reflex. Well, endocrine reflexes, there we go. Now, natural killer cells. Natural killer cells kill abnormal cells like cancer, called natural killers. I say they're natural born killers. This indicates infections. Most of these will indicate infections if lymphocytes are elevated. Now, so most of them will just be that. Now we have what is called monocytes. Monocytes are massive. They are 2 times larger than a red blood cell, so they're massive. They are agranular, though you could see but Ben loves money. They are considered agranular because they have few granules compared to others. They become macrophages, massive monocyte, macrophage, big eater, and they will leave the bloodstream to go to the tissues and become a macrophage. And macrophages phagocytize pathogens, things that can make you sick. They have a bean-shaped nucleus. When we look at the nucleus, we notice it's kind of shaped like a bean. They are also capable of being what is called an antigen-presenting cell. They are important to get T cells to recognize antigens. Helps the T cells to help it recognize antigens. It presents antigen to T cell and helps antibodies be produced. They indicate infections. Okay. White blood cells called acidophils. Acidophilic. They like acid. Eosin is an acidic stain. These guys kind of look like Spider-Man. They have what is called a bilobe nucleus and deep red granules. They are granular, Ben granular, B-E-N-E, eosinophil. They attack anything coated with antibodies as well, so they are phagocytic, NEM phagocytes, N-E-M-E, eosinophil. They fight parasites, so this can indicate worm infections. Parasites like worms, they release toxic compounds to kill worms. Allergic reactions also do this, and this controls the spread of inflammation. It tries to prevent the spread of inflammation. It prevents inflammation from spreading widespread all over the body, so that if you have an allergic response at one part of the body, it doesn't make the whole body swell. So I say they're easy on you, Phils. Eosinophils are easy on you, Phils, so they prevent the spread of infections. They indicate worms, that you have worms. Now, basophils, on the other hand, these guys are very basic. They're going to take on the dark stain, so they're basic lovers. They take on hematoxylin in a high level, so they take on basic stains. They are highly granular. They're so granular. How granular are they? They're so granular you can't even see the nucleus. It can make it difficult to see the nucleus. They're highly granular. But they do have a bilobed or trilobed nucleus when you can see it. These granules contain histamine and heparin. Heparin prevents blood clots. Histamine is a thing that dilates blood vessels. They stimulate the inflammation response, making it, they cause most allergic reactions. So I say basophils because they cause the spread of inflammation and cause inflammation. They are the bad on you phils because they're bad for you because they cause allergic reactions. So basophils are the bad on you phils. Okay. So I've done a little table here where I go and talk about each kind and get an idea about some things that you guys can see, and some stuff and differential counts, which you do not have to know the differential count for this particular course. It's something I talk about. I want to kind of prepare you, but you do need to know differential count, not specific numbers, but relative order. Never let monkeys eat bananas. Okay, and I put them in order. I always like to put them in order. And I made this little table just because I like tables. I like having tables that have everything in one little place, one-stop shop. All right. Now, let's talk about the production of this. What we have is called leukopoiesis. Leukopoiesis, white blood cell production. There is a stem cell that produces white blood cells, And this is a hemocytoblast. Remember, that becomes a myeloid stem cell or a lymphoid stem cell. Remember, myeloid stem cells become all of the white blood cells except lymphocytes. So neutrophils, monocytes, eosinophils, and basophils. Never monkeys eat bananas. Lymphocytes are from lymphoid stem cells. And that's your T cells, B cells, natural killer cells. All right, let's talk thrombocytes. Thrombocytes are usually these fragments of cells. They are cytoplasmic fragments. They're usually round disc-like fragments when they're floating around. They have enzymes and other clotting factors in them, proenzymes, enzymes that are called clotting factors to favor clotting, and proteins, and they lack a nucleus because they are actually fragments of a bigger cell. They live about 9 to 12 days. I should say 9 to 12 days. Sorry for the missing days. Before they're being removed by the spleen. Usually, mostly the spleen removes them. Macrophages in the spleen. There's about 150,000 to 500,000 of them per microliter. They are a cytoplasmic fragment. That was harder to say than I thought it was. They come from a cell called a megakaryocyte, and it's like a megakaryocyte. I like to think of it as like a plate, and then you drop the plate, and it breaks into several thousand pieces. The pieces are called platelets. And then when they're activated, we call them platelets. So they're cell fragments. Now, you only circulate 2/3 of them. You always have 1/3 of them as reserve. It's kind of like back in the old days of war, where you had the frontline troops and the reserves. And if the frontline troops got too many of them got killed, you'd bring the reserve units up and support them. There are still reserves, but they're a little bit different now. We do keep, combat troops in reserve so they can keep the battle going. Thrombopoietin is the hormone that causes the production. It's also released in the kidneys, called TPO. They are blood clotting. So, for example, if you have thrombopenia, too low, lower numbers of platelets, called thrombopenia, below 150,000, then you have excessive bleeding as a disease. Thrombocytosis is high numbers, and that can cause unwanted blood clots if you have over 500,000 per microliter. Now, platelets like to party. Platelets like to party. And when they party, think about a party, okay? When you party, you gather together, you stick together, and you clump together. These guys like to gather together, stick to damaged surfaces, and clump together. So they aggregate, they have adhesiveness, and they agglutinate. So they gather, stick, and clump. Okay. Platelets like to gather, stick, and clump. All right. Here is all the formed elements of blood with some ideas about them, giving the numbers about the abundance per microliter. The numbers that I've given. Now, I don't give it for every single one of the neutrophils, though I have their differential count ranges in the notes. So I do give it, but I do not make you memorize those. But you do need to know the other values that I've given. Now, RBCs, they come from RBCs, white blood cells, platelets, lymphocytes, all come from a hemocytoblast. And remember, myeloid stem cells are in the cell lineage of everything but a lymphocyte. Lymphocytes use lymphoid stem cells to produce the lymphocytes. Everything else uses a myeloid stem cell. Now, I do have a few colony-stimulating factors I mentioned, that MCSF. A monocyte colony-stimulating factor can stimulate the production of monocytes, and granulocyte colony-stimulating factor stimulates granulocytes. There are others, and I don't know if I should really have talked about or not. These are the ones I did talk about. I always try to pick and choose what it is I want to discuss based on some information that I think is important. All right. Now, here is the family tree for all these guys. Now, I want to mention a few things. We don't know, like some of these cells are like band cells that we might see. These cells, we are beginning to think, that it's more simple than this. It's potentially more simple than this. All right, now we're getting into a big thing, and that's called hemostasis. And we're going to settle in here a little bit, kind of settle in like a tick on a dog, and we are going to try to understand this. Hemostasis, guys, what is this? Hemo, blood. Stasis, stopping. This is called the cessation of bleeding. What is cessation? The stopping of bleeding. It occurs in 3 phases: vascular phase, platelet phase, coagulation phase. Vascular, platelet, and coagulation phases. Okay? Now, as we go through this, let's get an idea of what hemostasis needs. Hemostasis needs calcium, and it needs vitamin K, and blood clotting enzymes. It needs some blood clotting factors. I would say blood clotting factors. And I'm going to go ahead and put that there. This I did some editing on my notes, and I always try to edit my notes. And blood clotting factors. The clotting factors, which I'll talk about down here. Calcium ions and vitamin K are needed in almost in all part of clotting, especially coagulation. This is why if you don't give a baby a vitamin K shot, they can bleed to death. Their little thin, little sharp fingernails can cut them and they can bleed to death. Proteins like fibrinogen are needed, in enzymes like the clotting factors, coagulating factors. These are all enzymes. Almost all of the enzymes in blood clotting are what we call proteases, enzymes that break down proteins, and they help activate the protein. All right, so let's get started. Now, first thing I want to talk about is a little bit about blood vessels, and let's talk about it is let's talk about the vascular phase of hemostasis. Now, one of the things I want to do is talk about the vascular phase of hemostasis. Let's basically go in and look at a blood vessel, especially kind of a small blood vessel, and help us understand what's going on. All right, now what we have here is what is called endothelium. Endothelium. Now, not only that, we're going to have some cells in here that we should be generally familiar that are lining the walls of blood vessels. We know we have smooth muscle, okay? Then what we're also going to have is a connective tissue layer, okay? All right. Now, what's going to happen? This is a blood vessel. So here we have the blood. Blood's in here, okay? So what's going to happen is I get injured. And when I get injured, that opens up my blood vessel. And my blood vessel here has now been opened up and damaged. We have damage. And this damage here is going to start to cause bleeding. Blood can be lost from this, so we can have the loss of blood. And this bleeding that is happening here to blood loss needs to be stopped. So the vascular phase, we have this damage. One of the things this damage is going to do is these muscles are going to contract. And basically what they do is the blood vessels, muscles, they will spasm down, and that will help reduce blood loss. Okay, it will do what's called a vascular spasm, and that will reduce the blood loss. Okay, now how is it that this happens a little bit? Let's talk about what goes on during this phase. Sorry, I clicked the wrong thing. All right, So our vascular spasm happens when the diameter blood vessel is decreased, and that will help slow and stop the blood loss. Now, there's also a lot of things. The endothelium gets damaged in the things like that. And what's going to happen is there's other things. The endothelial cells, the damage to the smooth muscle here, this actually causes the vascular spasm. But notice that these endothelial cells have been damaged. Endothelial cells start to release chemicals that are important in the blood cessation of bleeding here. And one of the things damaged endothelial cells are going to produce is some adenosine diphosphate ADP. Now, what's ADP going to do? Here I have, later on, we're going to see my platelet. And we're going to see I've got platelets, and we're going to see this platelet is asleep. This ADP molecule, what it's basically going to do is it's going to be like a cup of coffee. And when this platelet comes by and gets this coffee, he is going to activate. That's what's going to happen to him. It's going to be like a cup of coffee, and he's going to be activated. Okay? Now, there's some other things that are going to happen. There are tissue factors that also activate platelets. Okay? There are these tissue factors. So let's say we got some tissue factor. And tissue factor and ADP, they are going to be like cups of coffee to activate this platelet. So this platelet now is fully awake and no longer asleep, and he's active. And when he's active, he can help plug this hole. So what we're going to see, the vascular phase will give rise to what is called the platelet phase. So we're going to see how this sets it up. And so what we're basically doing is we're setting it up. Now, there is something called prostacyclin. Prostacyclin, and then there's endothelins. Now, how did we get the vascular stuff? Let's talk about endothelins first. Endothelins are going to go to the damaged smooth muscle layer, and it's called an endothelin. An endothelin. And that's going to, endothelin is going to cause that to contract and spasm it down and prevent the loss. And the other thing it did, and I'm going to write it, these damaged cells, they make something called PGI2 or prostacyclin. Now, let's kind of describe it this way. Let's say you are a young kid again, and you guys are going back when you were a kid, and you want to invite your friends over for a sleepover. And you say, hey, I want to invite my best friend and my second best friend. And they're like, okay, that's fine. You can invite the two boys over and the two girls over to come over and stay with you, have a sleepover. He's like, but then I want to invite this person, this person, this person, this person, this person. And your mom and your dad's like, no, you can only invite those two. That's all we got room for. So that's like your mom saying, no, you've invited enough people over for the sleepover. We can't have any more show up. PGI2 limits the number of platelets that are going to get activated, so I don't activate too many. It's kind of like, hey, I want to have when I was in graduate school, I kept trying to pick committee members in my graduate committee, my thesis committee, and my major professor said no. He goes, he's like, graduate committees are not like birthday parties. It is not the more the merrier. You will have a hard enough time convincing us you should graduate. So, all right. So that helps you prevent making those kinds of things. So it's going endothelial cells, endothelins, PGI2 limits platelet aggregation. It prevents too many platelets from sticking. Now, something that's going to help the platelets stick is these damaged endothelial cells. What's going to happen is these endothelial cells, they're going to get a molecule stuck on them. And I'm going to kind of draw this out here. Is they're going to start getting this molecule, and I'm going to say VW. VW. And VW would get stuck on that. That actually, by the way, you don't have to know this, but that's called von Willebrand factor. That makes it sticky. Okay. Now, how does all this stickiness help? Well, let's see what this stickiness is going to do. Okay. In the platelet phase gets set up by vascular phase. Vascular phase does all this and sets the stage for platelet phase. So vascular phase will give rise to platelet phase by doing this. So we got all this sticky stuff. Now let's say I've activated these platelets now. So let's see what we can do here. We've got active platelets. And with these active platelets present, we've woke them up. We've gotten them up and woke up. They are all excited. They're woke up. And we've got all this sticky stuff here. All this sticky material that is all over this. These platelets, what they're going to do is they've been woken up. Remember, he was like this. He was very sleepy. He comes in ADP, for example, and tissue factors. What they're going to do is they're going to wake him up. And he's going to have all these little hooks on him when he gets woke up. And these hooks will catch. And you're going to start to get platelets coming in here. Remember, platelets, they like to party. These platelets come in and they gather together. They stick to surfaces and they clump together. And you get what is called a platelet plug. So let's talk about that a little bit. Now, what I want to help you guys understand is that this is important. The platelet stage happens, and these platelets, when the sticky area, they can stick to that exposed surface. That is called platelet adhesion. They then aggregate, and what happens, they form a platelet plug. So we activate them, we aggregate them, or adhesion, then aggregation. Now, platelet phase, these platelets, what they're going to do. Now, I like to describe it like this. One of the things these activated platelets are going to do is they're going to make ADP. They're going to start to make ADP. Now, let me kind of explain it like this. Let's say that your best friend throws a party. And your best friend texts you and says, dude, get over here. Girl, get over here. We're having a party. And they text you, we're having a party. So you go over to their house, and it's just you and them, and you're having a little party. But it's so good, you text one of your friends and say, hey, get over here. We're having a party. And they text their friends, and they tell their friends, come over, we're having a party. And next thing you know, the party grows. When you have activated platelets make ADP, this ADP activates more platelets in the area, and it keeps making it grow and grow. Now, remember, we're going to use PGI2 to try to limit that a little bit, okay? We don't want too many, but we want just enough. But this gets us enough to plug the holes. Thromboxane A2 keeps the vascular spasm going, called thromboxane A2, and serotonin. That's released from the platelets. We call these serotonin, remember, is a stimulatory neurotransmitter. Clotting factors that will help to also clot. Platelet-derived growth factor, which will start to heal the wound, and calcium ions. And calcium ions are needed for the platelets to stick. Basically, what the platelets kind of do is is they'll stick with calcium. So there's also all this calcium being released. I can't get everything in there in my drawing. Now, these platelets have formed a platelet plug. And we have what is called a platelet plug. Now, the platelet plug, these activated platelets, one of the things they release is clotting factors, and they also release calcium, Ca++. Now, what's going to happen is this is going to be able to lead these things to coagulation. And what coagulation is going to do, I've got all these platelets forming a platelet plug here. Then what I'm going to do is I'm going to take coagulation and happen, and I'm going to cover that with fibrin strands and reinforce it. Basically, that's what's going to happen. So let's look at how all this can happen. Now, here to show you what ADP will do, here I have platelet-rich plasma. Put ADP in it, and the platelets clump up. You can actually see that really well there. It's turbid here, cloudy here, clumpy here. Now, prostacyclin limits the platelet phase, PGI2, prostacyclin. And then eventually there are inhibitory compounds in the white blood cells that try to reduce this. And there's enzymes that break down ADP so that we can't activate more platelets. And this limits the platelet plug. Too big, this could cause unwanted clots. This could be problems down the road. Too small, it's not enough. Just right. So this is allowing us to get just the right amount of sealing that we need to have. Now, what's going to happen, these platelets are activated by ADP, and then there will be thrombin and exposed collagen fibers. So see, all this is there will be damaged blood vessels, and all of this stuff that's here can activate platelets, and they'll stick and they'll form a platelet plug. And coagulation cascade is going to help to do this. So what we're going to do is talk about coagulation next. Now, coagulation, this happens at about 30 seconds after an injury is coagulation. So as all this is happening, as platelets are being activated, those platelets release clotting enzymes that will lead to coagulation. Now, what is coagulation? Coagulation is the conversion of soluble fibrinogen to fibrin. Remember, when you see the suffix, the ending gen, you must be thinking that it's going to be activated. And fibrinogen gets activated into fibrin. Now, what's going to happen is, guys, there are three ways to do this activation of fibrin: extrinsic pathway, intrinsic pathway, and common pathway. Now, here's the deal. Both extrinsic and intrinsic can lead to common. Common's the one that you really need to happen. Now, others can lead to some things, but we're going to talk about the common pathway is the one you got to memorize. Now, the extrinsic is faster to activate the common pathway. They activate factor X, and the intrinsic more is reinforcement. Now, intrinsic versus extrinsic. Extrinsic is usually caused by external traumas, like getting punched in the face. Intrinsic pathways usually called by internal traumas, like a cannulus being added into a blood vessel, something damaged a blood vessel from the inside, things like that. Okay. So let's talk about this. So what we're going to do is coagulation. Now, with coagulation cascade, what I want to do is talk about with coagulation cascade. What I want to do is remember there is an intrinsic pathway and there's an extrinsic pathway. And there's X marks the spot. Intrinsic pathway can activate factor X extrinsic pathway can activate factor X. But what happens when factor X is activated? That's what we are concerned with here. I've activated factor X. Factor X is activated by 2, but pathways are activated, and this activates an enzyme called prothrombinase. Prothrombinase. We know it's an enzyme. So factor X activates what is called prothrombinase. Now, prothrombinase is going to basically take prothrombin and convert it to thrombin. Okay. Then thrombin, I keep clicking the wrong thing. It's always messing me up here. Okay. Then thrombin takes fibrinogen and converts it to fibrin. And this fibrin is these strands that reinforces the platelet plug. When I showed that platelet plug, I was like, here we have all these platelets just all gathered up here in a platelet plug. And I drew that out. I was like, here we have our platelet plug. And we had that damaged blood vessel. We had a platelet plug here. And then we came in and we laid all these fibrin strands on it and reinforced the platelet plug. That's what the fibrin does, okay? You will see this on the test, for sure. Right. So factor X is activated. Factor X activates prothrombinase. Prothrombinase converts prothrombin to thrombin. Thrombin converts fibrinogen to fibrin. Fibrin then is the coagulated blood, and that makes blood more semi-solid. Okay. Now, to block this, that's what a lot of rat poisons do, and you get a little nick and you bleed to death. So please understand this. It definitely is something you got to memorize. Now, I want to help you guys I'm trying to help you guys understand a complex process, because if you understand it, the things I'm teaching you, and you have it, you will understand it when you understand things like the blood controlling blood drugs that you guys will give in your fields. You will have to understand this. Now, clot retraction. What happens after the clot's been made? Blood is coagulated. Here we have very coagulated loads of fibrin strands. These are real fibrin strands right here. They have been made like Spider-Man's web has been cast, and it catches all of the cells and stuff in it. The clot contracts about 30 to 60 minutes it takes to break everything down. Now, plasminogen is activated by thrombin. So thrombin, something that thrombin does is it turns plasminogen into plasmin. Plasmin breaks down the fibrin clot. So not only does thrombin activate fibrinogen to fibrin, it also turns plasminogen into plasmin. So not only does it cause fibrin strand production, it also leads to the ultimate demise of the fibrin strands. It builds it, but it also tears it down. Kind of think about fibrin is like a construction worker building a scaffolding, doing the work, and then finishing it and taking down the scaffold. Now that he's built the wall back up, it's good to go. He doesn't need the scaffold anymore. There is a way to activate plasminogen called tissue plasminogen activator, and we give it. We call it TPA, or a clot buster. It dissolves and liquefies fibrin. Now, for example, there is a limited amount of time you can give TPA to a patient. You will learn about this. Now, case in point, my brother-in-law he worked in a factory, and he at his factory job he hits his thigh on a piece of machinery, and just hits his thigh, gets a good bruise on it. It hurt, but he went back to work because he's like, I'm a big tough guy, so he goes back to work. As he's working, he starts to feel really bad, and he's like, I'm having trouble, breathing, things like that. He's kind of feeling down, feeling like he's hurting a little bit. So he goes home. He gets home, he sits down in a chair, and he says he's sitting there and he feels like somebody runs a sword or stabs a knife in his lungs, into his chest, and he's in horrible pain. And finally, he lets my sister take him to the emergency room. Well, on the way, their daughter, my niece, is a nurse. And they told her what happened, and she says, "You need to give him TPA now." He had a pulmonary embolism. What had happened is he had hit his leg, blood clotted in a vein in the leg where he hit it. It broke loose the clot. It traveled to his lungs and went into a blood vessel in his lungs and got stuck there. And if they gave him tissue plasminogen activator TPA early enough, he survived it. Only 12% of people survive it. The kind of pulmonary embolism he had, the kind of PE he had. Okay. All right. Now, here's some definitely important things. We definitely got to understand heparin. There are anticoagulants like antithrombin 3. There's heparin, which prevents clotting by stimulating antithrombin. It inhibits thrombin, which thrombin activates fibrin, and it also stimulates antithrombin 3, which is an anticoagulant. Thrombomodulin, it activates a protein that inactivates clotting factors. PGI2 inhibits platelet aggregation, and TPA activates plasminogen. Know these. I might ask you guys one of them. It's very important. Like when you take blood in a sample and you want to test hematocrit, you have to heparinate that blood so it doesn't clot in the tube, and you heparinate it. All right, these aren't on the exam, so I'm not even going to read those. You guys can look over them. I always kind of have some disorders and diseases that I like to put. But guys, that's it. These are all of the clotting factors. I put them out there for reference, some information you might find useful when you guys go. Now, let me tell you something. I go over this, and I've been criticized by my fellow faculty. They say you teach too much, you talk too in detail. But one semester I was teaching this, and I'm going over it and explaining it. And outside the door was a nursing professor who was coming to visit the class to recruit my students. And they were standing outside the hallway listening to the lecture. And they came in after it was done and they said, "I wish someone had taught me that." I said, "I was in nursing school. They act like we know this, but most people don't cover it." You guys, I know it's harder, and then I'm putting things in front of you, and you may talk to your friends and say, "Well, my friends in so-and-so's class don't have to learn this. My friends at the university don't have to learn this. Why me at a community college having to learn it?" Remember, it's my job to prepare you as well as teach you. I will teach my guts out and help you understand it. But guys, I hope I helped you understand it. This should be really all there is. And guys, if you want to do that review, definitely do. And guys, thank you so much. Here you can actually see a basophil. You can actually see the bilobe nucleus of a basophil. Anyway, guys, thank you so much. I hope I helped you, and I hope I helped you understand it. But as always, thank you so much for watching. I hope you guys do well, be safe, and continue on, and don't give up. Keep going. Thank you, and have a good day.